In section 3.2, as you can see here, we're going to be looking at subsequences and Cauchy sequences. And as I mentioned in the last section, or in the last lecture, these are concepts we should be familiar with from not so much calculus, but introduction to analysis courses or analysis on the real line, if you have taken those courses. Otherwise, this may be a bit challenging learning it the first time. So make sure you reread some parts, read the slides, maybe the section from the book, Principles of Analysis by Walter Rudin, to pretty much digest these ideas, these definitions, the theorems that are in the section, and just overall understand the concepts presented. So with that said, we'll move on to what a subsequence is. A subsequence, so given a sequence P sub n, consider a sequence n sub k of positive integers such that n1 is greater than n2, greater than n1 is less than n2, less than n3, less than so on and so forth. Then this sequence P sub n sub I is called a subsequence of P sub n. If P sub n converges, its limit is called a subsequential limit of P sub n. Actually, right here, this is supposed to be a little subscript. P sub n sub I converges. So if P sub n sub I converges, its limit is called a subsequential limit of P sub n. We'll look over a few examples. So here we have the sequence 1 over n. I guess I'll write mother sequence. Mother sequence. Sorry about my bad handwriting. That says mother sequence. If that's a mother sequence, so to speak, this would be a subsequence. Subsequence, I'll just write it like that. And subsequence as well. So we have 1 over n. So the range of this sequence is 1, 1/2, 1/3, 1/4, 1/5, so on and so forth. A subsequence would be 1 over k squared. So it'd be 1, 1/4, 1/9, 1/16, so on and so forth. So it's basically just choosing some of the terms of the sequence. 1 over 9, somewhere over here, and then 1 over 16, more outside, and so on and so forth. So a subsequence could just be basically looking at the mother sequence and just take away some terms. It may be that you take away no terms. A mother sequence is or just a sequence, I should say. A sequence is a subsequence of itself. Another example of a subsequence is 1 over 2k. So 1/2, 1/4, 1/6, 1/8, so on and so forth. That is a subsequence of 1 over n because we only pick certain points in the range, meaning we only pick 1/2, 1/4, 1/6, right? As opposed to all 1, 1/2, 1/3, so on and so forth. So that's an example of a subsequence or subsequences, I should say. So we have a theorem. If P sub n converges to P sub n converges to P if and only if every subsequence of P sub n converges to P. What does that tell us? That tells us that a sequence, if it converges, then it has the same limit as each of its subsequences. Right? So every subsequence converges and they all converge to P. And that happens if and only if P sub n converges to P. That is a theorem, not a proof. I do go over this proof, but in an introduction to analysis course. Not here, I'll leave the details to you. The biconditional shouldn't be too hard to prove. But because we're going to present this theorem coming up. But before I do need to go over these two lemmas. So first one, we have gone over this, so this shouldn't be anything new. If E is an infinite subset of a compact set K, then E has a limit point in K. Right? We went over compact sets last chapter. Also, if P is a limit point of a set E, then every neighborhood of P contains infinitely many points of E. Okay, so now we can present our theorem. As you can see, there's going to be an A and a B. So A says if P sub n is a sequence in a compact metric space X, then some subsequence of P sub n converges to a point of X. And that is kind of already sounding similar to lemma 1. So just keep an eye out. B says every bounded sequence in Rk contains a convergent subsequence. Okay, so we're going to go ahead and with the proof. And I'm going to prove A, and I'll just help you with B. I won't prove it, but I'll help you, give you a clue that will pretty much give it away. So first A, let E be the range of P sub n. Well, if E is finite, then there's a P in E and a sequence n sub I, where we order all the n's as shown here, such that all the terms of the subsequence are equal to each other, and they equal the limit. Right? So that evidently converges to what? To P. So that's kind of like the not interesting case. Now the interesting case. Well, if E is infinite, then from the first lemma above, E has a limit point, P in X, right? Because X we said is a compact metric space. So by lemma 1, P is a limit point. We're calling that limit point P in X. Now we're going to choose N1 so that the distance between the limit point P and the P sub 1 is less than 1. That's how we're going to choose N sub 1. So having chosen N sub 1 all the way to N sub I minus 1, the second lemma, what does it tell us? That there's an integer N sub I greater than N sub I minus 1, such that the distance between that limit points and the points of the subsequence P sub N sub I are less than 1 over I. Right? So, well, that tells us that P sub N sub I converges to P. For part B, or for proof B, this pretty much follows using A, and you can also use the fact, sorry, you can use part A, and you should use what we looked over, the Heine-Borel theorem, along with the third thing that included. So if a set is closed and bounded in Rk, then that set is compact. And that also implies that every infinite subset of that set has a limit point in that set, right? So I would look over that theorem from, I don't think it was the last lecture, but the one before that. 2.4, no, 2.3 should be. I believe it should be 2.3, where we looked over the Heine-Borel theorem, where three statements were equivalent. So we'll move on. Whoa. Oh shoot, I forgot to put that. So I suppose let's ignore that for now. Let me go slower. This slide doesn't have much. Uh, it just states the theorem. The subsequential limits of a sequence P sub n in a metric space X form a closed subset of X. And I'm not sure why I don't have that. That doesn't look pretty. But as a matter of fact, let me. Oh my gosh. Give me 1 second. I'm trying to see if I can erase it for now. No, this would take forever. Okay, I suppose we can ignore it. Let me just cover it up a bit so it doesn't distract us. So we should be, let's understand this theorem. What is this theorem even saying first? I guess that's good enough. Okay. Okay, so we have the theorem saying that the subsequential limits of a sequence P sub n in a metric space X form a closed subset of X. So there's a not interesting case at first. Let E star be the set of all subsequential limits of P sub n, and let Q be a limit point of E star. We have to show that Q is indeed in E star. So we're going to choose n sub 1 such that P sub n sub 1 is not equal to Q. Simple enough. If no such n sub 1 exists, then E star has only 1 point, and well, there's really nothing to prove. Right? Because then Q would be in E star. Now, more interesting case, the case where E star has more than 1 point. We're going to let P sub n sub 1 not equal Q and put delta equal to the distance between Q and that point P sub n sub 1. Suppose n sub 1 to n sub I minus 1 are chosen. That's going to be clear as to why we're choosing them. Well, since Q is a limit point of E star, there's an X in E star Give me a second. Let's do it like this. Just so we don't get ahead of ourselves. Well, since Q is a limit point of E star, there's an X in E star such that the distance between X and Q is less than delta 1 over delta times 2 or over this should be a delta. So since Q is a limit point of E star, there's an X in E star such that the distance between those 2 points, X and Q, is less than delta over 2I. Right? So since X is in E star, there's an n sub I greater than n sub I minus 1, such that the distance between X and that point, P sub n sub I, those points are less than, again, delta over 2I. What does that tell us? Well, then that the distance between Q and P sub n sub I is less than or equal to 2 to the 1 minus I times delta for I 1 to infinity. It says that P sub n sub I converges to Q, so therefore Q is indeed an E star. This proof may be a bit difficult if you're not too comfortable with subsequences. Other than that, it should be fairly straightforward. Make sure you read it, digest it. Nothing too difficult. But we'll be moving on to Cauchy sequences. Again, you might be familiar with this concept. A sequence, P sub n, in a metric space X is said to be a Cauchy sequence if for every epsilon greater than 0, there's an integer, capital N, such that the distance between points P sub n and P sub m is less than epsilon when n and m are greater than or equal to capital N. So you know how convergence, we had said that points get arbitrarily close. Let's say this was our limit points. Our points of the sequence, x sub n, are getting arbitrarily close to our limit points here, P. Well, Cauchy sequence says, forget about the limit point, where there's no mention of a limit point. But as a sequence increase, or as soon as n and m become greater than big N, these points get arbitrarily close to each other, right? So P sub n and P sub m, the distance between those 2 points is less than epsilon, meaning points get arbitrarily close. So as a sequence increases further than capital N, points get arbitrarily close to each other, not necessarily to a limit. I should say that in our discussion of Cauchy sequences, the following geometric concept is going to be useful. So here, let's kind of like see that the geometry, there's a Cauchy sequence, this distance red, is greater than, let's say, distance in green, which is greater than the distance in orange, which is greater than the distance in blue, so on and so forth. But anyway, these points are getting closer and closer to each other. How close do they get? Well, if it's a Cauchy sequence, they get arbitrarily close. That's what a Cauchy sequence is. Okay, so now we bring in the definition of a diameter. Let E be a non-empty subset of a metric space X, and let S be the set of all real numbers of the form distance between P and Q, where P and Q are both in E. Then the supremum of S is called the diameter of E. Right? So let's say all these points are now in E. E is equal to the union of all xn. Or actually, I should just put E is equal, E is the range of x sub n, meaning it's all these points. This point, this point, this point, all those points. That is E. What is the diameter of all those points of the set E? Well, the diameter of E, I'm going to erase it here, is we take all the distances between, so this point, we take this distance, this distance, this distance, so on and so forth. What's the biggest one? Probably from x1 to x6 is probably what looks like the biggest distance. But we also have to consider now all these distances. So from x2 to x3 to x4 to x5, so on and so forth. Right? And then what's the greatest of those? And then so on and so forth. You pairwise, you take all the distances and whichever is the biggest one is the radius. So the radius of E, let's say this was indeed the biggest distance, this would be the radius of E. Radius of E. Right, and it would make a circle or something. But that's what the radius is. Now, I do want to point out, it does say supremum here. It doesn't say maximum, it says supremum because the range of a sequence, or actually even just a set E, I shouldn't even say sequence, E can very well be infinite. E is just a subset of a metric space, so it may very well be infinite. So that's why we take the supremum of S, and that is called the diameter. Okay? This here is pretty much a theorem, but I put it in black just because we're not really going to prove it. It's just something we should notice. It's kind of another way of looking at Cauchy sequences. So if P sub n is a sequence in X, and if E sub n consists of the points, well, P sub n plus 1, so on and so forth, then P sub n is a Cauchy sequence if and only if the diameter of E sub n as n goes to infinity is 0. What is that telling us? Well, this here is basically saying keep going in the sequence and then keep taking the diameter. What is the diameter? Well, because it's Cauchy, these points are getting arbitrarily close to each other. Right, so as you take it to infinity, the diameter is pretty much going to be arbitrarily small, which is why as n goes to infinity, the diameter of E sub n is 0. So it's just pretty much another way of looking at Cauchy sequences. Now we're going to have two theorems. So if the closure of so if E bar is the closure of a set E in a metric space, then the diameter of E bar is equal to the diameter of E. Also, if K sub n is a sequence of compact sets in X, such that these compact sets are nested, and if the limit of the diameter of Kn as n goes to infinity is 0, then the intersection of all these sets, K sub n, of these compact sets, consist of exactly 1 point. And that should be pretty intuitively clear, although the proof may not be so easy. Shouldn't be too difficult either. Don't let me scare you. So first, we're going to prove the first one. Since E is a subset of E bar, right? Every set is a subset of its closure. Well, then the diameter of E is less than or equal to the diameter of the closure. What else do we need to show now? Well, that we need to show this as well. So fix epsilon greater than 0 and choose P to be in the closure of E and Q to be in E. By definition of the closure of E, there are points P and Q, or P prime and Q prime in E, such that the distance between P and P prime is less than epsilon, and the distance between Q and Q prime is also less than epsilon. I'm staring at this because this doesn't look, I believe there should be, actually I'm pretty certain there should be a bar here as well. That would make sense. So by the definite, right. Okay, so because they're in the closure, they have to be limit points. So there are points P and Q, sorry, P prime and Q prime that are arbitrarily close to it. Why? Because if they're in the closure, that means they are limit points of the sets. Well, therefore, we can use, suppose a triangle inequality, the distance between P and Q less than or equal to distance between P and P prime plus the distance between P prime and Q prime plus the distance between Q prime and Q which is less than 2 epsilon plus the distance between p prime and q prime. Again, because this here was less than epsilon and this was less than epsilon. Now, well, that's less than or equal to 2 times epsilon plus the diameter of E. So nothing too confusing yet. Well, it follows that the diameter of the closure of E is less than or equal to 2 epsilon plus the diameter of E. But epsilon is arbitrary, right? So we can make it arbitrarily small, showing that this is the case as well. Therefore, the diameters are equal. Oh, now we move on to B. So we're going to put Q equal to the intersection of all these sets Q sub n. And we know I've been saying Q all this time. Sorry, put K equal to the intersection from 1 to infinity of K sub n of all these compact sets. So Q sub n are compact sets. And we know Q isn't empty. And why is that? Well, we actually saw a theorem in the section of compact sets telling us that if K sub n are compact sets, the intersection is non-empty. So if it helps, go back and look at that theorem. But we know that this intersection, this finite infinite intersection, is not empty. Well, if K contains more than 1 point, well then the diameter of K must be greater than 0. But for each n, K sub n contains K. So the diameter of K sub n is greater than or equal to the diameter of K. But that contradicts the assumption, right? That Kn goes to 0. What does that tell us? That tells us that in fact Kn consists only of 1 point, right? So we assume that there were 2 points and we reached a contradiction. Therefore, our theorem holds. Next thing we're going to be looking at is some theorems. These might be a bit long, or I shouldn't say long, but these are of the section. So first one, in any metric space X, every convergent sequence is a Cauchy sequence. That's a huge, huge theorem. Really, I guess, popular one. It's a really well-known because, well, Cauchy and convergent imply each other. Also, if X is a compact metric space and if P sub n is a Cauchy sequence in X, then P sub n converges to some point of X. And finally, in Rk, every Cauchy sequence converges. Okay, so proof of A should be, it's fairly straightforward. If P sub n converges to P, and if epsilon is greater than 0, well then we just get that the distance is less than epsilon. Just basically, definition of convergence is always we're stating. Therefore, the distance between P sub n and P sub m by the triangle inequality is less than the distance between P sub n and P plus the distance between P and P sub m, which is less than 2 times epsilon. Epsilon is arbitrary, so we get that P sub n is a Cauchy sequence. Simple enough. This next one is probably the most involved proof of B. So if X is a compact metric space, and if P sub n is a Cauchy sequence in X, then P sub n converges to some point of X. So let P sub n be a Cauchy sequence in a compact metric space. For n equal to 1 all the way to infinity, let E sub n be the set consisting of P sub n plus 1, so on and so forth. Then as we saw, the diameter of the closure of E sub n is equal to 0 because, well, we just saw that, right? So being a closed subset of a compact space X, each E sub n is compact because another theorem we saw. If you can't remember that theorem, it's a theorem that states that closed subsets of compact sets are compact. Also, these sets are nested, so the closure sets are also nested. Well, the theorem in the last slide, right, shows that there's a unique P in X, which lies in every closure E sub n, right? We saw that it consists of one point, all the intersections. So that point lies in all of them. So now let epsilon be given. All right, so we're good so far, nothing too complicated yet. Well, by the equation above, there's an integer n sub naught, such that the diameter of E sub the diameter of the closure of E sub n is less than epsilon if n is greater than n sub naught, right? So when I say equation, I mean this equation. By that equation, there's an n naught such that that diameter is less than epsilon. And since P is in the closure of E sub n, it follows that the distance between P and Q is less than epsilon. For every Q in the closure of E sub n, therefore Q is in E sub n. In other words, distance between P and P sub n is less than epsilon, right? If n is greater than or equal to n sub naught, which tells us that it indeed converges. So what does it say? Well, it says precisely that P sub n converges to P. Finally, our last one. Let Xn be a Cauchy sequence in Rk. We want to show that this sequence converges. Okay, so we're going to define E sub n as we did above in part B. Right, but instead of pi, we're going to put, so here, this is what I'm talking about. Let me erase here because I'm just saying stuff and not really pointing out. So we're defining E as we did over here. E sub n consisting of all those points. But instead of P sub I, we get the X sub i's, right? So instead of these, we get X sub i's. Well, for some n, the diameter of E sub n must be less than 1. The range of Xn is the union of all those E sub n and the finite set X sub 1 all the way to X sub n minus 1, right? The ones we excluded. Now we're including, so that's the range of X sub n. Therefore, X sub n is bounded. Right, because we know E sub n diameter is less than 1 and finitely many points. We can easily bound that. And we actually saw something similar in the last lecture. So therefore, X sub n, and this should be bold. I don't know why it's not. X sub n is bounded. And since every bounded subset of Rk has a compact closure in Rk, well, our theorem just follows from what we just saw above. right? That it indeed converges to some points of the space in Rk. So again, we're using a lot of stuff from B here. We're letting our sequence be a Cauchy sequence, but instead of Pn, we have Xn. We're using this for defining E sub n, similarly to this, and we're also using this equation. Right, so I shouldn't say B is a more general case of C, but as far as like intuition goes, it may help you a bit, but try not to think of it like that. Just make sure you understand these, digest them, like I said. These are the meats of this section. And I mean, actually, I don't know if I could even say that because this next slide is also really important. We're going to be looking at an extremely important definition. That definition is the definition of complete. So a metric space in which every Cauchy sequence converges is said to be complete. And last slide, what did we see? Well, we saw that all compact metric spaces and all Euclidean spaces are complete, right? We showed that those Cauchy sequences in those spaces did converge. Right, so we can say that every closed subset E of a complete metric space is complete. But what's an example of a metric space which is not complete? Well, a metric space that's not complete is, let's do the space of all rational numbers with our metric distance between x and y is absolute value. Here, every Cauchy sequence doesn't necessarily converge. Okay, one last thing we're going to see are monotonic functions. So a sequence S sub n of real numbers is said to be monotonically increasing if S sub n is less than or equal to the next term, S sub n plus 1. Wait, what did I say? Monotonic sequences, right? That's what we're talking about. S sub n, again, monotonically increasing if S sub n is less than or equal to S sub n plus 1, meaning the term that's next is greater than or equal to the previous term, or monotonically decreasing if the next term is less than or equal to the previous term. So if a sequence stays constant, it is monotonically increasing and monotonically decreasing because we don't have the strong equality there. So that's what monotonic sequences are. Okay, so we have one last theorem before this lecture ends. Suppose S sub n is monotonic. Then S sub n converges if and only if it is bounded. So this is a biconditional proof. One direction, extremely simple. We already know it actually. Right? We know from last lecture that every convergent sequence is bounded. So we only really need to prove that if S sub n is monotonic and bounded, then it converges. So suppose S sub n is less than or equal to S sub n plus 1, meaning that we have a monotonically increasing sequence. And the proof is analogous in our other case if it were monotonically decreasing. So I'm just going to do the increasing case. So let E be the range. of the sequence S sub n. Now if S sub n is bounded, we'll let S be the least upper bound of E, right? It's a supremum of E. Well, that means that all the terms of the sequence must be less than or equal to R supremum, right? That's just the definition of least upper bound. Well, for every epsilon greater than 0, there's an integer n such that s minus epsilon, we can get a term of the sequence S sub n that's between s minus epsilon and s, our supremum. Otherwise, s minus epsilon would be our upper bound. And that's not the case because it's s. Right, so we can always find this s sub n. Since s sub n, the sequence increases n greater than or equal to capital N, therefore implies that s minus epsilon is less than s minus n, less than or equal to their supremum, which shows that s sub n converges, right? It gets arbitrarily close to s if n is greater than or equal to n. So that by definition shows that it converges. And it actually converges to s, And as I had said before, the other direction, every convergent sequence is bounded, so we get the other direction. So that should wrap up this lecture, where next time we're going to be looking at upper and lower limits, and then some special sequences that are pretty fun. You might have seen something similar in calculus too, but we see them in more detail.